All right, so let's calculate the refractive index for a substance if the speed of light in that medium is not 2.91 times 10 to the 8th meters per second. All right, we'll set up a nice easy equation. Remember this one right here. The refractive index is equal to the speed of light in the vacuum divided by the speed of light in the medium. 3e to the 8 divided by 2.91 e to the 8. This is a nice, simple, easy question. All right. 3e8 divided by 2.91 e8. And we get the refraction is equal to 1.03. And that's our answer. All right, next one. An angle of incidence of 40 degrees in diamond results in an angle of refraction of 27.8 degrees. Is the second medium more or less optically dense than the first medium? Well, let's think about this. What question would we use to solve this? Or what formula would we use? It's quite simple. It's actually quite obvious. We would use Snell's law, right? We're told that we get an angle of incidence of 40 degrees, and we're told the medium that we're going through is a diamond, and if we remember back to our first page, we have a bunch of indexes of refraction. Now, if we plug the index of refraction in for the diamond into Snell's law, we'll actually be able to find the second medium's index of refraction. So let's solve that real quick. We'll say that N1 is equal to, N1 sine theta 1 is equal to N2 sine theta 2. Let's plug in our numbers right here. We know that N1, the N for a diamond, is 2.45. And we'll go multiply that by sine of 40. And we'll say that's equal to N2, which is sine of 27.8. So to find N2, we'll just go N2 is equal to 2.45 times the sine of 40 divided by sine of 27.8. All right, let's see what value we get for N2. We'll go 2.45 times the sine of 40. We get 1.57. And we're going to divide that by the sine of 27.8. And we get that N2 is equal to 3.38, actually, if we round it up. 3.38. So N2 is equal to 3.38. So we get an index, so we get 40 degrees in diamond results in an angle of 27.8. And an angle of incidence of 40 degrees in diamond results in an angle of refraction of 27.8. Is the second medium more or less optically dense than the first medium? Oops. All right. Is the second medium more or less optically dense than the first medium? All right, well, first of all, I don't really like the way that this question is worded at all, to be completely honest, because it doesn't tell us which is the first and which is the second. I'm just assuming that diamond is the first. And if we assume that diamond is the first medium, that means our second medium has an index of refraction of 3.38, which means it is more optically dense. The higher index of refraction, the more optically dense it is. What optically dense means, or what you should really think about that is, think about the density of water versus the density of syrup, right? If you were to try and trudge through water versus trudging through syrup, which would be harder? Obviously, walking through syrup would be a lot harder than walking through water. So it's the same idea for light. This index of refraction, this value for N, is how hard it is for light to go through the substance. So, that being said, the second one Having a larger index of refraction means it's much harder for light to move through it, means it is more optically dense. So N2 is more optically dense. What is the N value of the second medium in the above problem? Well, hey, we already found that out. N2 is equal to 3.38. What is the wavelength? What is the wavelength of an electromagnetic wave in space with a frequency of 98,300,000 hertz? Easy problem. We know it's an electromagnetic wave, so that means that it has a velocity equal to c equal to 3e to the 8 meters per second. If we just plug this into our basic formula, v equals f lambda, we will find our wavelength very easily by just dividing the velocity by the frequency. So we can just rewrite this as lambda is equal to v over f, and we'll just plug in our numbers right here, 3e to the 8, and this is 1, 2, 3, 4, 5, 6, 7, 9.83 e to the 7. Do that. Let's go 3 e8 divided by 9.83 e to the 7. Then we get 3.05 meters. Remember, all of your wavelengths are going to be found in meters. Okay, let's look at number 13. Question number 13. While standing near a railroad crossing, a person hears a distant train horn. According to the train's engineer, the frequency emitted by the horn is 440 hertz. The train is traveling towards the person at 30 meters per second, and the speed of sound is 346 meters per second. Draw a picture of this event, label the direction of the waves, the observer, and the source. Okay. Let's see. Letter A. So we're going to do this just like we did question number 3. Let's see. We have a... Let's read this again. Standing near a railroad crossing, a person hears a distant train horn. According to the train's engineer, the frequency emitted by the horn, the train is traveling towards the person. All right, so I'm just going to draw the front of a train right here. All right. There we go, the front of a train. All right, that sort of looks like a train. And this is, we'll draw some smoke billowing out just so we can give it some flavor. Smoke billowing out. And it is playing out a horn, and it has at 440 hertz. So let's draw some notes flying out of there. All right. That's like a toot 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 toot. That's sort of like that was back in my music days. All right, so this is emitting sound this way, and here we are at a railroad crossing. I'm just going to draw an ear again. Here we are at a railroad crossing. So the sound is going this way, and we know that our train is also going this way. So label the direction of the wave. We've labeled that. The observer. The observer is just standing here. I'll give him some eyes. He's perking up his eyes because he's like, oh, wow, there's a train coming. And the source. So, all right, we're labeled. We are good. We are done. Letter A is good. What is the actual frequency that reaches the listener's ear? Again, we'll just very easily set up our Doppler shift. So FO is equal to Fs multiplied by V minus VO over V minus Vs. Now, our source is equal to 440 hertz. The velocity of the wave, which we get from the question, is 346 meters per second. The velocity of the observer is equal to 0 meters per second. And the velocity of the source is equal to, there it is, 30 meters per second. So we'll just plug this all into our equation right here to find the frequency that the listener hears, or the frequency observed. So FO is equal to 440 multiplied by the velocity. Actually, I'm just going to write the velocity of the sound, 346. Now remember, since the observer's velocity is 0, we will just leave it and take it out of the equation. So we'll write 346 minus 30 right down there. Because it's a positive velocity, the train is going in the same direction as the waves. That's a positive velocity. So when we plug it into our equation, it is subtracting from the velocity itself. Okay, 346 minus 30, 346 divided by 316, multiplied by 440, we get a frequency that we observe of 481.8 hertz. And just like that, question 13 is done. All right, let's flip over to the back. So the question is asking us what happens to the velocity of light as it enters water from air. Well, we talked about this a lot, but remember, when something has a higher index of refraction, and I'm actually going to grab our first sheet so we can look at this. When something has a higher index of refraction, it means that it's more optically dense, as we said before. And being more optically dense, it means it slows down the speed of light. It slows down the speed of light because there's more molecules for the light to pass through, for the light to get through. So what happens to the velocity of light as it enters water from air? That's easy. It slows down. What happens to the wavelength of light as it enters water from the air? Well, to compensate for light slowing down as it enters a new medium, the wavelength will actually get shorter as well. So the wavelength shrinks. And what happens to the frequency of light? Well, the frequency is going to stay the same. Frequency stays the same. The wavelength and the velocity change to compensate for one another. So draw and label a transverse wave with amplitude, wavelength, crest, and trough. A transverse wave, as we know, is a wave that looks like this. So I'm going to put a dot on each node, and a node is just when the wave crosses the middle line. That's all a node is. So draw and label a transverse wave with amplitude. Okay, here's our amplitude. And I'm just going to make a little mark right here. I'll say amplitude. Wavelength. Remember, our wavelength is from crest to crest, trough to trough. Any two equal points. Wavelength. Crest and trough. So this is a crest right here. And this is a trough right here. Next question is draw and label a compressional sound wave with wavelength compression and rarefaction. All right, this one you guys might not recognize and understand immediately, but I promise you, you know this. So a compressional sound wave is, if you'll remember from very, very in the beginning of the unit, is like, is like this. So here's our compressional wave. So if we want to talk about wavelength, remember our wavelength is right here. These are points of compression. And this is the rarefaction. So hard for me to do those. Hang on a second, I can do it. There we go. Rarefaction. So wavelength, rarefaction, and compression. This is a compressional sound wave. This is really what sound waves look like. Not like this. Sound waves aren't transverse, but they're more compressional. All right, last question. Here we go. Describe how red light and low-pitched sounds can be thought of in the same way. Now, the hint to this is Doppler shift. Remember, Doppler shift, or the Doppler effect, sort of affects both sound and light. Now, if I could write this down, that'd be great. Doppler shift. The Doppler effect affects both sound and light. So describe how red light and low-pitched sounds can be thought of in the same way. Well, remember, as an object is coming towards the observer, we experience a higher pitched sound or a larger frequency. But if the source is traveling away from the observer, we actually experience a lower pitched sound. That's how the Doppler shift works. Now, think about it in the same way as light. If light and the source are traveling towards you, you're going to experience a more bluish light, all right? Because the frequency is going to be appear to have more frequency. But as you go away, right, we're emitting light, a star is emitting light, but it's traveling away from the observer, we're actually seeing it as it's sort of reddish. It's red shifted. So you can experience red light and low-pitched sounds as a consequence of the Doppler effect. So describe how red light and low-pitched sounds can be thought of in the same way. They both are a product of the Doppler effect. And that's the test review. Any questions, go back, watch these two videos. I think you guys will do great.